Okay, so I got to purely for Argo 2 over the summer, and one of the things that I got to do then was to kind of help to do some grading, and this worksheet came out as a result of what I saw. Students were not able to grasp certain concepts, and it just kind of confused them. Everything just went all over the place. So I wrote this worksheet to help them point out their mistakes. Suffice to say, even though I didn't get to interact with you guys this semester, because I'm not an Orgo 2 peer leader this semester, but I got to, I'm just assuming that, these are the same things that you might be encountering. So I just decided to give you this worksheet to try. As you can see, this was prepared over the summer, right? Orgo 1 students who were with me as well in the summer, well, this is what I was doing. Okay, I've also included a predicting the reagents this time, because sometimes you might not know when to use certain reagents. You just throw it into the reaction, make sure you're hoping for the best, and that's wrong. So you need to identify. There are some characteristics of a starting material that tells you how a reaction proceeds, right? Okay. What else? Yeah, so mechanisms wise, I would not be able to cover them all, but for like micro addition, what else? I have, yeah, like stuff like micro addition, I would probably write the mechanism out, and then I'll post them together with the answers, probably, hopefully before midnight, because I still have answers to write for Orgo 1, and as soon as that's done, I'll get you guys. Your exam's at 3:30 tomorrow, I know, so rest assured that everything I have today will be posted before then, okay? At least by tonight. All right. And of course, the usual predicting the reagents is going to be fair game. And I want to focus more on the retrosynthesis. Just a show of hands here, who was struggling with question 5, like this question here on page 7? Anyone managed to solve it? No? Okay. Yeah, it's normal. This is a hard one. Yeah. All right. Okay, so without further ado, let's go ahead and get started. Oh, sorry, just to show our hands again, who is here for the first time, so I know how to adjust the pace that I go at. Sarah, Shane. Okay. Yeah, so one more housekeeping thing is if you have not registered, like for example, Shane, I don't see your name on the registration sheet, just go ahead and do it at the MSLC website. It's just for tracking, so we kind of know if this program is good. We can get more resources to help future students next semester. That would be really, really helpful if you could do that for me, right? Thank you. Okay, let's see if there's anything else. So yeah, like this is an addition to alpha, beta, and saturated carbonyl, right? Again, the mechanism is just something that I'm gonna post at the end of this review. The answers here is just for you to see what's going on if you got the right answer, because I did not give an answer key. So, okay, let's go ahead and get started. For this one here, you should have something like this, right? It's also really similar to, there's one more, what's it called? Robinson annulation. It's really similar to that. If you have not, if you're not familiar with that mechanism, please check out my old video from exam 3, because I went through that mechanism there. Okay. Of course, what else am I missing is the phenyl group. Phenyl group comes out here. Okay. All right. This is a Claisen rearrangement. Right. So remember always to draw the chair. Vanillic is always at the bottom, so we know that vanillic is right here, and because it's sort of like trans to the alcohol, sorry, to the oxygen, right? trans right here. So it's going to be trans right here. Okay. I have a video actually that goes through this mechanism. Let me go ahead and put the link in the comment box so that you guys can see that after today. All right, I'm just gonna go ahead and put it here. So go check it out when you have the time. Okay, and allylic is at the top, so we have this double bond here, and because isopropyl is sort of like cis here, so we know it's gonna be up here. Okay, at least draw these intermediate steps if you're not sure of what's happening, so that you can get some partial credit. All right, and then we're gonna do our rearrangement. Just gonna bond here to get this here, right? So my phenyl, nothing changes on my substituents. They remain the same configuration. Okay, and the isopropyl is at the top. Now we're gonna look from here, and we see that the isopropyl is facing on the plane, but my phenyl is facing out at me, right? Where I'm looking at the eye. So what kind of relationship do we know this is gonna be? Syn or anti? Yeah, it's gonna be anti, right? So just gonna linearize it. That was really horrible. Sorry about that. Okay, so we have the phenyl right here, and the isopropyl group right here. And then this is a hydrogen atom here. Okay. All right, the third one. What's the first step and the second step? Anyone knows what kind of reducing agent this is? It reduces NH2 to NH, right? So if I use this, if I use sodium cyanoborohydride, I think that's what it's called, I can't remember, right? Which one gets reduced? Does the carbonyl get reduced? No, it's only the amine that gets reduced, right? Because this is a milder reducing agent. Okay, so why I put this question right here is because I had students last semester that were reducing the carbonyl as well. Okay, so please don't do that. You might get like fluster in the exam, but take it one step at a time. Okay, so we have an amine here. Correct. And then steps 3, 4, and 5. I have silver oxide, right? So that kind of tells you have an elimination reaction. It's a Hoffman elimination, actually. Okay, 1, 2, 3. Yeah, it's a Hoffman elimination. And Hoffman from your Orgo one should tell you that it's at the end of the molecule, right? Okay, number 4. Let's see. Who here says that this is the answer for number 4? Anyone? Just show of hands if this was your answer. Why is it not right? Because, yes, the OH group is acidic, right? Mr. Grignard here has a problem with alcohol. He just goes for it. So, oh, that's actually really good. You guys got to see it this semester. Last semester, I had a good 5 people telling me that that was a product. And I was like, oh my gosh, no. Okay, so yes, under acidic protons, you cannot have a Grignard reagent going in. Excellent. Because this deprotonates. Okay. All right, so what we have here is this reagent forming a ring, correct? And notice that this carbon right here has a methyl sticking out. So this is when you see this reagent here on an amine, what it forms, it's always a Markovnikov addition. Let me just verify that. Hang on 1 second. Right? If you see my exam 3 notes, yes, it's a Markovnikov addition. Okay, and it has to have an amine on one end and a double bond on another end. Okay, so this is something that you have to look out for. You do this reagent when you deal with this reagent here. Okay, has an amine and an olefin. So, and then right here is an amine. And then you're able to form that product. Okay. Anyone here knows what we're forming? What's the end goal here? This is a what? Endo, right? So we are using the Fischer endosynthesis. I just need you to go one step before. So you should have this here. Okay, this should be a starting material. All right, fun fact. This endo that you're seeing here, okay, his name is Scato. Scato is what makes your poop smells like poop. And yeah, so you kind of learn how to make poop in Orgo. It's pretty fun, right? Okay. All right, so now, right here we have how many carbons on our product? 1, 2, 3, 4, 5, 6, and 7. Okay, so right here I have 1, 2, 3, and 4. And because this is a Michael addition, which I'll show you in the mechanism when I upload these notes, right, you should know that it's just a simple ketone that you're going to start off with. All right, and then the next step. Okay, so this here, is this Kumada or Suzuki? I hope you guys remember the circle of life. It's boronic acid, so it's Suzuki. So what we know is that, okay, this is exactly where it came from, and I know that my starting material has to be something like this here. It has to have two R groups, right? And of course, it has to have a bromine because this is where it attaches onto the coupling reaction. But I also have this reagent here, stannous chloride. What does that do? It reduces what into NH2? Yes, it reduces NO2 into NH2. So this is how you know you are starting from this here. Okay, come, let's predict the reagents for this one. There are three answers. Here's your hint. If you gave me any of these three, you are absolutely right. Right, and then you have water and, okay, this is known as the Wolff-Kishner reaction. And then what else can you use? Or anything else? You could just use zinc or mercury and what? Hydrochloric acid, right? Or you could use let me see, this one, and then rainy nickel. Why? Because you're getting rid of the carbonyl, correct? So yeah, you could use the Clemmensen reduction. This is it. This is, here is the Clemmensen, which is a good thing because you don't need to know the mechanism for that. Okay, so Clemmensen, rainy nickel, or with Kirchner would get you the same answer. And the reason I put this here on the exam, sorry, on this study sheet, was because people were saying I could use H2 and PDC. Well, that's not possible, right? So please don't do that. All right, the next two questions are something that I kind of like asking students because, well, I want to test your knowledge and your understanding of what's going on. Okay, what functional group are we working with in question 2 and question 3? We have what? We have a carboxylic acid, and this becomes an ester. So when a carboxylic acid becomes an ester, you're going to use the Fischer esterification. Okay, Fischer esterification, and that means you're just going to use your R group in a protic form with an acid, right? And then the bottom one, what are you dealing with? This is an ether, right? Can I use lithium aluminum hydride here as well? Can I do that? What would happen? Yeah, it would reduce both, right, into the primary alcohol, so that's wrong. You can't use that. You can only use a milder reducing agent so that we reduce this ketone into an alcohol. And then we're going to use the Williamson ether synthesis. And then we're going to have benzyl bromide as the finishing material. Okay, so please take note, if you're making an ether, you're going to go and use the Williamson ether synthesis. If you are making an ester, please try to avoid as far as possible from using Williamson ether synthesis conditions on the carboxylic acid. Just know the difference between these two. The OBU, Where did the OB go? So see, this is untouched, right? It's an ester. So we use some reducing agent with sodium borohydride. So NABH4 is not strong enough to reduce this into an alcohol. But it's strong enough to reduce a ketone into a secondary alcohol, and from there we can conduct the Williamson ether synthesis. Okay, be careful. Yeah, that was I should have used a different functional group for that, but oh well. Okay, what about the next one here? So should be simple enough. You have a carbonyl and you have a secondary alcohol. Any oxidizing methods that you've learned is acceptable. Swern. Please don't write that. Like write out the reagents consisting of Swern. You could use PCC, PDC, Tempo, or DMP if you have learned that. If you have not, then don't bother. Step 2, well, it's just simple. Because you have an acid chloride, you just need to put water and it gives you carboxylic acids. All right, here comes the fun part. Now we are going to work on retrosynthesis. Okay, so I don't know what's your favorite way of approaching a retro problem. Oh, sorry. Let me know when you guys are good to go. Ah, good catch. Yeah, I honestly didn't even notice it myself. Okay, so what's the last step? Since we forgot, yeah, it's just sodium and liquid ammonia. Okay, this is the Birch reduction, something that you learned just after conjugated pi systems, part of your first exam. All right. Okay. Thanks for letting me know. Yes, this is on. I'm currently recording it right now, and these will go on to. I'll share the link with you guys after. Okay, so let's go ahead and do retrosynthesis. I know they're kind of hard, but let's see. We have 5 to pound out, right? Okay, we should be able to get them done pretty easily. Okay, so you have a more complicated molecule on the left, as you can see. That kind of tells you it's not. It's easier to go backwards, right? Or at least I think it is, because, or if you want to go forwards, we can work towards this starting material. That's fine as well. Okay, so let's just go forwards then. We know that acid chlorides come from carboxylic acids. So go ahead and this is my train of thought. Okay, we'll see if it works, but suffice to say, I can make a carboxylic acid turn into an acid chloride and using thionyl chloride in heat. Okay. So how can I make this into a carboxylic acid, right? I have, is this an electron donating group or an electron withdrawing group? Or what kind of directing effects does it have on the benzene ring? How does it map out? Ortho, para, or meta directing? Yeah, it's ortho and para, right? But because we want it to be in the para position, so let's just assume that we are able to get this in the para. So you're going to use bromine in iron or FeBr3, ferrobromine. That's fine. I just usually put Fe, right? And then here, what can we do? It's a 2-step process. So you're gonna do a substitution reaction, right? Get rid of that bromine, make it cyanide, and water. Okay, why I would prefer this answer over the magnesium and carbon dioxide is because I didn't give you a step 4. This is only 2 steps, so you have to try to conform to what you have on the exam. But I don't think you're gonna get the points taken off if you wrote. I'm just gonna put here also okay. MgO, THF, and then CO2, diethyl ether, and then doing the normal acidic workup that you guys are always used to. Okay, so these are fine as well, but I just kind of prefer conforming it to the number of steps that they gave you. Okay, so I have an acid chloride. I have now this guy to deal with. Correct. So look at this though. I know that. Sorry about that. I know that this here is an ester. Correct. With an ester, I know that a step before this is something called the Baeyer-Villiger oxidation. So what am I adding here? I'm adding exactly the same thing, right? And I already have an acyl chloride, so I just need to add one more starting material of mine in the presence of aluminum trichloride. And there we go. This is how we get to that next intermediate. And then step 6 is super easy. Baeyer-Villiger oxidation, right? I just said it. What's that reagent there? Starts with M, ends with CPBA. This is called the Baeyer-Villiger oxidation. When you turn a ketone into an ester, you use MCPBA. Yeah, it's exam 2. So I believe this is exam 1, this is exam 2, exam 2, exam 2, right? So I hope through this retro worksheet, when I designed it, I made sure to incorporate as much as the older material as possible. Because if you realize, especially from the practice exams that you have, older material, retrosynthesis usually stem off the older material, right? We can't give you sugars, right? It doesn't really make sense to work with. So it's easier for us to just test you, or for examiners to just test you on older material, which is why I place quite a heavy emphasis. So for polymers, though, I'm not too sure. I think if anything, you might just be asked to draw the mechanism. I'm pretty sure there might be a mechanism question. Do you guys learn Grab's catalyst? Did you guys do that? Or did you guys do Ziegler and Natta? Do you guys do this, Grab's catalyst, or any of these? So this one has I think this is, and then this one has, I forgot what the thing is. I don't know, because I don't know if you guys were able to get through everything. Oh, okay, so you guys went over Grubs. All right, I guess that's pretty much, yeah, exactly. PCY3, something like that. I can't remember it offhand, but yeah, this is pretty much Grubs catalyst. Okay, so I think you have to worry about Grubs more for a reaction mechanism, if anything. All right, so this is what kind of reaction? Diels alder, right? I have a conjugated pi system here, and I have, so we call this dienes, and we have a dienophile. So with dienes and dienophiles, we will get what? Remember the transition state for this? I have to make sure that my, let me see. Draw this easily here. I have to ensure that I have my secondary pi overlap, correct? So one here, and then I have another orbital, sorry, from here that's going to overlap. So because of that, we have the endo product. It's going to be anti. ME. Okay, please don't forget your stereochemistry. If you draw the exo product, it's going to be wrong, right? And then, so we want to get from here down to here now. What do we have? We have an ester going into an aldehyde, and we have an alkene going into an alkane. So these are two pretty straightforward reactions. One of them is even for orbital 1. So hydrogen and PDC. Question, will Wilkinson's catalyst work here? Will it work? Yes. Will Wilkinson's catalyst work on this? No. Okay, good. So you guys know what the conditions are, right? Anything more than 2 substituents over an alkene, it will not work. But for simplicity, let's just go ahead and just use palladium and carbon. And I have an ester going into an aldehyde. Exactly, Derek. Well said. That's exactly what's happening. How do I get from an ester to an aldehyde? Starts with D. Ends with ebol, right? And water. Okay. Do take note though, especially for those of you guys who do research or work in labs. Typically, this reaction, Dibble, is really nice on paper, but in the lab, it's like, at least from what I read, I'm like a nerd like that. I kind of like reading papers on orgosynthesis. A lot of scientists or researchers report that this only gives a 40% yield because it kind of goes straight to the alcohol. So just fun fact. Why does number 2 does not work? I still don't get it. Which part are you talking about, Sonia? For this retro, which part are you lost at? Oh, it won't work if you had more than, so over an alkene, right? This is an alkene, this is an alkene, this is an alkene, right? As soon as you get more than 2 substituents, right? Tri-substituted and tetra-substituted alkenes, they don't work with Wilkinson's catalyst. But in this case, yes, it works. I just chose to use H2 in PDC. But if you wrote Wilkinson's, it's also fine. Okay, so Dibble on carboxylic acids, I don't really recommend you doing that. If you have to make an aldehyde from a carboxylic acid, reduce it down to an alcohol and then work it up. And that's another thing. Yeah, like don't worry too much about Dibble. All you need to know is that it converts esters into aldehydes. There are 2 ways you can get from a carboxylic acid into an aldehyde. So step 1 is to reduce it. And then step 2 is to oxidize it up. Or you could use a Fischer esterification. Just use methanol and H3O plus. Remember, this is just any R group, right? You can use ethanol, you can use isopropanol. The point of this reaction is to get it into an ester so that you can use Dibble. Reduction in PCC. Yeah, if you wanted to go that route as well, Dhruvan, you are not wrong. Go like I said, okay. But make sure you use lithium aluminum hydride because sodium borohydride is not strong enough. All right, so now I have I have amines coming into play now. Okay, let's see. So I know that this can be made from what? Seems like the previous step from this year is gonna be this year, right? So I can do this, right? This would work, and then I would have my intermediate, and then how do I reduce it down into, exactly, good job. So then, boom. Okay, so we have two smaller ones at this point. Again, we are working with Diels-Alder reactions, or rather conjugated pi systems, not really a Diels-Alder, but this is more of a co-arrangement. Okay, yeah, I know it can be confusing, but did I give you any intermediates? I did not. Okay. What I did give you though is the stereochemistry here. So I know that at some point I need to rotate the bond, but it's okay. Let me go through the steps with you and then we'll work it out. Okay. So we have a 6 pi electron system. Right? So right here we have Cn. Okay, let me see. No, I think it's easy to go backwards so we can figure out what kind of configuration we're going to use here. Okay, let me work backwards. We know that this is an ether, so ethers come out from what reaction? We're going to send ether synthesis. Great, so we need an alcohol in the previous step. Okay, and because we're dealing with a 6 pi electron system, we know at some point we need to get this here, right? Well, we just don't know. Oh, sorry, this is wrong. We need to get it there at some point. But we just don't know if this is dashed or is it hashed, correct? But we know that it's going to be a ring, of course. So the previous step from here, I know that, I hope you guys remember some of your Orgo 1 reactions. Maybe that's why you could have been stuck, because you forgot to incorporate your Orgo 1 reaction, right? We have a cyano group here, right? And, oh, sorry. Let me see. Oh, okay, I think I know what happened. I'm missing a BR here, I'm sorry. Okay, now it makes sense. Okay, I need to make this here. So I have to cut off this bond, right? So I have a Br and an OH here. It's okay. I admit this is a hard one. Took a while. So we have OH and Br, right? And we know because this is now syn, that means we have rotated the bond, right? If I'm going to put them back onto a ring, then therefore they have to be anti to each other. Okay, so two things happen here. I have an OH and a Br, OH and a Br here, right? And I have two cyano groups that I have to invert one of their stereochemistries because I'm rotating it about this bond here to go back to a ring. I'm trying to make it as close to the ring as possible. Okay, so now I know how I can get from here to here because it's an anti-addition. So I'm going to draw my 6-pi electron system. So I need this to go up, I need this to go down so that they're anti to each other, right? Which means my orbitals have to be here and here. And then I just got to fill it in with the rest, correct? 1, 2, 3, 4, 5, and 6. So when we have this here, we know it's going to be under light conditions because we're going to go conrotatory for a 6-pi electron system, right? 6-pi electron system, now we know we formed this here. So we have, let me just be consistent, cyano group here, cyano group here. And Derek, you're absolutely right. From here, we're going to put, this is a halohydrogen reaction, but it has to be the thermodynamic product. It's at 60 degrees because we have the double bond. This is a 1,4 addition. So 1,4 addition gives us exactly what we wanted here. And then when we cleave it off with ozonolysis, right, we open up the ring. And then from there, it's just a simple Williamson ether synthesis. And there we have it. Okay, so if it's xylenes and heat, okay, which means to say that you have to look at the orbitals, right? The orbitals that I shaded right here are up, down, down, up, down, right? Which means that this tells me this is what? I have enough energy to raise up the HOMO one level up, correct? Because like normal 6-pi electron systems, you know, it looks like this here. 1, 2, 3, 4, 5, 6. And this is under normal heat conditions. But under light, I have strong energy that can raise it up by 1. So I pop over to this orbital configuration instead. Because if it was heat, look at what happens here. Up, up. Oh, sorry, this is 4 pi. One, two, three, four, five, 6. So up, up, down, down, up, up, right? They're going to have to rotate this way. So when they go together, this is conrotatory. Sorry, this is disrotatory. All right, so disrotatory gives me, then this would go up. This cyano group goes up, correct? And then this cyano group goes up. So it's going to be a syn addition. That's wrong because what we wanted was an anti-addition. Okay, so draw the orbitals if you're not familiar with determining it. Because honestly, if you ask me, hey Ian, 6-pi electron under light, is it this or I would not be able to tell you. This is why I draw the orbitals, right? Because orbitals tell me that, oh, as long as it's alternate here, I have enough energy to go up one level. So therefore, I have to use light and not heat. Okay. Okay. Let's see. let's come back to this later. I want to do this question first. Okay, whenever you see stuff like that, when you see a double bond right here, make note of what's to come, right? How have you learned how to make double bonds? Starts with W but sounds like a V. It's called the Wittig reaction. This kind of stinks of Wittig here, right? And what else do I see here? Oh, I see a cyclicized molecule from something that does not look remotely similar. So that kind of tells me I might have to use a strong base, right? I have to employ enolate chemistry at some point. Okay, so let's go ahead and look at this here. I gave you this. This is also another hint here. Right off the bat, you should be able to know that I'm dealing with Naomi and her homies. Strong base, right? And what happens here is that under this condition here, I have this, whoops, right here. Okay, and then from here to here. So the next hint I gave you right here is plus CO2, which means that I have generated an extra carbon, or rather, I split my molecules into two, of which one of it is CO2, right? So I have to chop off this bond here so that I can make CO2, and the only thing that allows me to do so is ozone. So what I have here is now a diketone. Okay, with aldehyde here. And now, if I want to cyclicize them, right? It's pretty straightforward. Remember, how do we know which is the alpha carbon? It will be the carbon that gives me the most number of rings, correct? So you have to figure out in your mechanisms. If I deprotonated a hydrogen here, would I get a 5-membered ring? Or if I deprotonated this hydrogen here, how many membered rings would I get? Okay, so this is something that you just kind of play around during the exam. But we know that because we want a 5-membered ring, we're going to use Naomi and her homies again, right? And okay, look at this part here. I have an amine from a double bond, right? How can I possibly do that? It's a simple substitution reaction at some point, so I would have to give it something to substitute with, right? Usually NaCN DMF. Okay, and then from here, I can make it into into an amine. How can I make an amine from a cyano group? Yeah. Yeah, I will draw the mechanism when I upload the notes onto. This is something I will show the mechanism. It's a Robinson annulation problem, basically. And don't worry, my notes are gonna be like I will explain things in my notes as well, so you don't have to worry too much about it. Right? I can use lithium aluminum hydride, and then work it out with acid or water. Okay. And then from here, look, I have a ketone and I have um, an olefin, right? So let me just write this here. So now I know I can do a normal Wittig reaction and phosphorus elite with this should be methyl right here. So positive, counter ion, strong base. Okay, so yeah, this is basically the hard one, or so I thought. I think the other one was harder because you have to figure out the Kanshi. But don't worry about it. The whole point of this retro problem is to was designed to help you study the material at the same time. Okay. So let's see. We're adding 1, 2, 1, 2. So okay, let's see. We have no carbons here, but we have 1 carbon here, 1 carbon here. So this is going to be 1 here, 1. Oh yeah. No, no, no. Sorry, sorry. No, 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 no. It's right. It's right. If it was just this, right, then you would get this. Okay. No, you're good, Derek. Yeah. So yeah, just take note. Okay, let's do the last one. You guys probably should be tired by now with all the retro problems, but I figured I think I might just give you the answers for this, just so you know to how to work on it, because I don't deny it's pretty hard. Okay, so we want to make this, we want to focus this on here, right? And what we're going to do is to put bromine in water at 0 degrees, because at 0 degrees we get the kinetic, the kinetic product here. Go ahead and oxidize it to with anything you like. Right here. Okay. And now predict the reagents for me here. I think you should be able to do this part. Step 3. What are we gonna do with step 3? Jesus, take the wheel. Yeah, what's that NH2 thing? It's called the Wolff-Kishner reaction. Right? You can use Clemmensen reduction as well. That's fine. Or you could do you could do the Raney nickel. All right, and then the last step is just a simple Kumada reaction or Suzuki, whichever you prefer. And there you have it. That's pretty much that's the answer. You could also use this as well. That's fine. That would be the Kumada one. Okay, so there you have it. That's pretty much the entire solutions to this worksheet. I hope you guys feel better about it. Like I said, this worksheet was kind of designed to kill, because that's the trade-off. You want to try to incorporate everything that you've learned from the first semester, from the first week till now. It's hard, I admit, but thanks for sticking with me through this. I will be posting the mechanisms, as I said, for selected parts of the reactions. I hope this benefited you guys, at least for those who attended this for the first time. You're very welcome. Yeah, and unfortunately, I didn't get to see a lot of you guys in person this semester. I only know some of you, but it's been a pleasure. Oh, Mudar, you're here. Hi, long time no see. How How likely is there gonna be mechanisms? Yeah, you can expect mechanisms for sure. You might, I don't know, like at least for my final, I had the Zimmerman track square one as well. So remember, what's the golden rule for the Zimmerman track square one? If you see this here, can you just tell me? Please let me go to bed at night. What goes in this box? Thank you. Hydrogen is always axial. Okay. Yeah. So study that. Get to know some of your Ziegler Natta or your Grubbs catalyst. I think Grubbs catalyst uses the circle of life, if I remember. But let me see. Is there anything else? No, actually, that's pretty much it. So I'll leave you guys be. Like I said, it's been a pleasure teaching you guys. All the best for your exam. If you see me around the school, just say hi. At least let me know who you are. And for those who came, please register on the MSLC website, just so that I have some form of tracking here. Let me give you the link. It would be so useful if you could just put the thing there.